All right, so we are at the right moment here in terms of this is something which you will need some clarification or help. So as I was mentioning, difference between a cycle, of course, in a directed graph is going from one node to the other and then being able to go from the other node back to the original one. That's the cycle's definition. But the loop, which is what of interest to us, which is single entry structure, is different. And compiler uses some very interesting ways of detecting a loop, which is very, very efficient. But that doesn't detect all possible cycles, which are multi-entry. So this exercise will tell you that if you really aim at detecting all cycles and not just single entry loops, but multi-entry loops and so on, and in general, any cycle in the graph, in the control flow graph, then what is the effort that you will have to expend? Because Warshaw's algorithm is the lower bound in terms of these. And it will cost you more compilation time. It will also yield more structures because not just single entry loops, but multi-entries and in general, any cycle. And so we are asking you to find out how much more you can detect at what compilation cost. So this is a bit of an involved thing. It also does not change LLVM IR. The good news here is you can start with a structure, traverse it, build your own structures which are in your passes, which import the information and do all this stuff there. But you're not altering the IR. The IR alteration needs LLVM certification. In other words, LLVM maintains very strict standards of compliance of an IR, and so none of these involve any of that. The last exercise in this particular set of things is involving restructuring the IR, but a very simple restructuring, and this is to be done before the IR is changed into SSA. What we are asking you is a very simple transformation here. As we'll see again in next couple of weeks, week actually, I would say, is that the join of in the control flow graph where the incoming branches merge onto a basic block, that's the source of problems in terms of analysis. It makes the analysis a little bit more approximate because we are combining information and reduces the precision of the analysis. And we'll see the details there. So the transformation is simple. We are asking you to replicate the basic block on all incoming edges, and all the outbound edges are also replicated accordingly. And therefore, we remove this join inside just one function, which is the most time-consuming function. We'll identify that first through profiling. And that's where we'll do this only inside the loops, and all the loopness there and the details are there. So this will need transformation, but the transformation is simple. Again, as I said, it's a control flow restructuring and replication of basic block. There's nothing else there. So even that exercise is simple and should commit properly. Now this should be done before the SSA generation, because we don't want any fee nodes and other functions to be present. After this, the SSA should be generated, because essentially we are removing some joins here, which are sort of the SSA functions. So just follow that and identify the right place in the IR. And then, so we want you to find the benefits of this in terms of how the optimizations are bettered. We have given you a couple of them to track, and also the execution time, how it improves. So that's basically the overall project, and this is to give you a very good view of how the compiler phases interact, how the data structures are held, and how they should be restructured, and so on. And I expect you to pretty much finish this pretty well within about 10 days, 12 days, but we have added a little bit more time, about 4 or 5 days, just in case anybody runs into any problems, etc. But get started and follow the same sequence. Go with the simplest things first, get those out, and more involved things you will get as you go further. This is, of course, a homework, not a project. And so this is to be done individually, and so that all of you are able to learn the LLVM's interesting IR and so on. And there are documentations there. I'm not saying it is very deeply documented, but it's there to a high level. And then finally, code navigation. So that will help you to identify which phase is where of the LLVM and what IR is present there. Once you narrow it down that this is where I need to do my changes or my instrumentation or my transformations, then within that, it's a matter of navigating the C++ code. It's a very heavy duty C++ code, very well written. And of course, there is a deoxygen is the best bet to navigate that. There cannot be anything better than that. So, so good luck. Please take advantage of Piazza, Nathan, and hopefully nobody will face any problems there. So this ties very well with the topics that we are covering. So let's get back in there. So basic block detection is where we were last time, and then finish the control flow graph. Hope all of you had a chance to read this also from the things in the book. This is straightforward algorithms in terms of detection of leaders, and we had explained it in terms of how they work. So of course, just knowing basic blocks will allow us to do certain within a block, but not across, because we don't know which block we are going to or coming from next. And so an example of that analysis could be that in this case, 4 times I, statement number 3 and 4 times I within state number 5, they are redundant. The second one is redundant because I has not changed, and we are re-evaluating exactly same expression. So that kind of redundancy and can be captured and eliminated by just reusing the value in T1. And that's another reason why not to regenerate or reuse T1s and recycle a temporary. For example, in statement 4, we could have generated an IR, which after doing indexing operation on A here, you can see that the purpose of T1 as such is served. So on the left-hand side, we could have reused T1, being clever. But if we had done that, then obviously the value in T1 would have been lost, which is at statement number 3, and would not be available at statement number 5. So that is the reason for not reusing temporaries and trying to recycle temporaries. We keep generating newer temporaries. And that doesn't mean that, of course, we'll have such a huge amount of data storage need because of each of the temporaries. Most of the temporaries will get absorbed through register allocation. And then, of course, the leftovers will be allocated on the stack if you don't have room for them in registers. That's how that temporary will get managed. Many of them will get even purged further by some optimizations such as copy propagation, etc., even constant propagation, etc. So this space will be managed properly through register allocation, and also intermediate optimizations like copy propagation and so on. So at this point, we'll generate these temporaries, making sure that they are all new, that they're not recycled. And this is also the basis for single assignment. You can see that each temporary is assigned only once here. So that value of the temporary is not erased. So in other words, this T1 is written here, and even if there is no redundancy, this T1's value is available throughout over here because it's never erased by any reassignment to T1. So that's one point I wanted to mention. Now, of course, across the basic block optimization, they are not possible unless and until you generate the IR at next level. And that's where we did all this further transformations or identified the edges which are fall through as well as control transfer edges because of conditionals and unconditional statements, branches. And we had again gone through this. This is where you use the labels, like label 3, to decide that there is a branch between 12 which goes to 3. And of course, this being a conditional branch, there is a fall through edge which will keep going from 12 to 13. Similarly, fall through will exist from 2 to 3 because that's a successive basic block. The control comes from the top, executes, and then just naturally goes into the next statement. So these are the two types of fall through edges. One is after the conditional branch, and there is a second one which is a regular statement. If, of course, there is an unconditional branch, which means that there is just like a go-to statement, then of course there is no fall through edge. So only in that case you don't have to generate that, or you should not, of course, generate this. So so this is the flow graph that we had built last time, and it's shown at abstract level by the left hand side as B1 basic block followed by B2, which is a loop, and then that is exiting finally into B3. Now you can see that this representation is of course hierarchical. Inside B1 we have these two statements, B2 has so many statements, and B3 has that statement, and so on. So the representation that you will see in LLVM and any other compiler in terms of the linear IR that we had is now transformed into a graph-based IR. So the top level is the graph, and inside each of the blocks is, of course, a sequence of IR statements. Now we could stay with this representation, which is very useful for doing certain analysis, transformations, and so on, by propagating the information from one basic block to the next and going on a particular path and so on. But many times our interest is in, of course, performing some of the optimizations like the one which I have mentioned in the exercise, that we want to replicate these basic blocks and remove the joins and so on, only inside loops. So we need information about, hey, I want to just focus on loops and just do this transformation because that is where my most benefits lie. Most of the execution of the program happens to be inside the loops and not in the acyclic regions. So why worry about modifying B1 or B3, for example? Only B2 may be of interest to me in terms of optimizing it. Maybe there are some statements there which are not changing values. Maybe some redundancy can be removed. Some other dead code might exist there, things like that. And all of these are there for targets of different types of optimizations or constant propagation I may want to do only within B2. And so we want to identify the loops as the candidates for targeting the optimizations. Now, it doesn't mean that we can just confine the analysis within the loops. I want to clarify that, because in order to maybe even optimize the loop, for example, in this particular case, I may need to know with regard to I, what is the value of I that is coming in from B1. So I may need to do certain analysis which might extend outside the loops, but that information will be, of course, finally used only for carrying out transformations within the loop. So there is a difference between what analysis I may have to generate in order to transform a loop, and of course, what do I transform using that information. The main goal here will be to transform the loop, make it more efficient, and therefore not really worry about changes to B1 or B3 and so on. But at the same time, in order to transform B2, I might need some information which is coming out from the loop, or maybe even going out of the loop. So, and we'll see some examples of these, which is called as loop invariant code motion, in which we'll need to gather some information in order to be able to optimize it. So in short, in order to do the what we call as optimizations which are very targeted, we may need to discover more structures, and that's the goal of the next phase, which will now try to do something on the control flow graph and discover regions of interest to us. And that region of interest could be mostly a loop. There are certain other regions of interest sometimes, which I will mention as we go along. And they also allow us to do certain quick analysis and optimizations without really iteration of propagating the information, because they don't have such iterative structures which are there. Before we get into that, in general, a control flow graph could be a multi-graph, which is shown because of the fall through edge and this combining through the two in the same basic block. And in general, you may say that, oh, let's get rid of one of the edges, and what's the point of having this same edge between the two, or multiple edges between the two graphs? This is not any general graph. This is really a graph which is carrying some information with it. So for example, if it's a false edge versus a true edge, there are different pieces or outcomes of the predicate which are being indicated by those edges. And so depending on the analysis that you undertake, you may need to preserve this information and not really get rid of it just because they are between the two different basic blocks. For example, if you're interested in finding out, and we'll see again later, an analysis which is something called as sparse conditional constant propagation, your interest may be the edge which has become live, because that is the predicate which is evaluating to in a particular way and carrying the information along that edge to the next basic block. The other possibilities, you may be doing a path sensitive analysis, which is not just doing one basic block to the other, but might be following a certain path which connects these basic blocks and propagating information along them. And in such cases, of course, there are two paths here. One is on the false side and second is true, and they should be separated in terms of the information. So, coming back to our original proposition in terms of identification of loops, at this particular level, the loops can get formed because of course, our source level structure and some branches and all kinds of different things. And we want to discover this particular piece of information for the reasons I mentioned earlier. And we want to do this fast. So one possibility is, of course, that take your source level loops, keep track of all of those, and then generate or keep this information annotated during the control flow graph generation, etc. And of course, there we are relying on the programmatic constructs such as for loop, while loop, etc. to detect a loop. Um, but many times there are nesting structures. There are also loops which can get formed because of, it's very rare, but certain other transfer of controls like if then else kind of branches or go to kind of transfer of control. And so in order to unify all that, but be able to detect this quickly and keep language independence in some ways, we have a loop detection as a necessary pass in pretty much every compiler to focus on the regions. And we don't want to, in general, detect every cycle in the program, but a loop. So what is exactly a loop? So a loop is a structure like this. Let me fast forward a little bit, which is shown over here through this particular diagram. What it is basically a single entry structure. In other words, the control, if you focus on node number 2, what is going on here is the control is coming from outside of the loop into this something which is the node 2. Now there could be multiple predecessors to 2. That's not the point. But necessarily all of them are entering this region of cycle at this particular node called 2. From there, we are going to, of course, take this going from 2 to 3, 3 to 4. There is yet another loop which is formed at 4. You can see it here, which is 4 to 5 we go. Then there are 2 branches, DAG, and the 8 loops back and so on. And then you can see here that the inner loop 4 is entered at 4, again via 3. And then it exits when the predicate, there's a predicate there, obviously at 4. When the predicate becomes true or false, depending on how the loop is written, it exits from 4. It doesn't stay inside going to 5. It exits, go to 9. And from there, the loop again continues on the outer side back to 2 through another branch from 9 to 2. And again, there is a predicate at 2, which might become true or false, and the outer loop will exit and go to 10. So you can see that when you write programs, typically using while loops or for loops, or your favorite repeat until, any kind of iterative structure, you will be writing a loop which is entered at a basic block through a well-defined point which starts the loop. Before that loop is entered, typically you do initialization. So take a for loop, for example. The first part of that for loop is initialization, which is something like maybe 1. The basic block 1 captures that. Going back to our example, let us look at how this looked. So look at this particular loop. So all the initialization code for this loop, prod equal to 0, I equal to 1, that stays in basic block 1. Now from there, the loop is entered at B2. It does some things there to the values which are coming from B1. There could be, as I said, multiple predecessors coming from B1, but all of these will eventually enter here. Maybe there are different initializations and so on, but they will all enter at B2. From there, the B2 things will execute, do some things to it. At the end of this, you will check if the predicate is true or not. If it is true, it will branch back. Otherwise, it will exit. So you can see that there is a cycle which is formed here, but it is not any random kind of a cycle. What it is single entry cycle. In other words, through a well-defined interface to the loop, we enter it at one point, at one basic block, we iterate, and then we exit. There could be multiple exits. This one is showing only one exit going through B3, but you could very well imagine a structure inside where there could be multiple basic blocks, and some predicate might exit it using that particular basic block, exit outside that loop at one point or the other point, and things like that. Very So why is this particularly the case in terms of programming languages? Why do they generate single entry loops? The reason is this, that imagine a loop which can be entered at multiple points. It will become very ill-defined in terms of the initialization that has to occur and so on. And the whole loop structure will become, if you allow the jump in the middle of the loop will start executing in a very ill-defined way. And so through a careful design in terms of constructs and other things, the such structures are disallowed. Now, how can one write such a loop, which is multi-entry? One can certainly use some gotos and jump in the middle of loop and so on. But such programs, of course, are very ill-defined. Many languages very strictly prohibit the jumps within the middle of such loop, any loop, for preventing semantically ill-defined code. So in other words, during semantic analysis, such check is made if in the middle of any loop there is any jump from anywhere, and of course it is a semantic error and the program doesn't pass the language restrictions. So due to these reasons, and with structured programming in terms of the use of constructs and so on, and also go-to-less programming, so to say, which is another thing which was heavily promoted. The programmer is forced to use these source level structures, which result in loops, which are what we call as single entry, which are very special types of loops, which enter at a given basic block. So what is a single entry means? The entrance is at a single basic block like B2 here. And from there, the loop can go inside its body, it can take multiple control paths. And then from there, eventually it can go to a basic block or basic blocks. And all of them will branch back into B2 for that particular loop, which is a loop back edge. And then in the middle of the loop or the body of the loop, exits, control exits, depending on the predicate values, which will terminate the loop and which will go outside the loop. So given this special structure such as this, which is called a single entry structure, the question is, how can we identify such special single entry loops, which are 99.999% cases, as you will see in this exercise that I have given. The multi-entry loops are pretty much non-existent, almost zero such cases. So given these special types of cycles or single entry cycles, I want to call them loops, how do we identify them? So the interesting thing here is this, that they all entered through this well-defined header, what we call as the entrance of the loop. And there is a special property of this header, which we are going to use, which is called as the dominator of a given region of a program. So you can see here in this example, and then we'll get into formal definitions of how to actually find this information. Any time you want to go to any node within the loop, you have to necessarily go through this entrance of the loop to reach it. For example, if you want to go to 4 from 1, you definitely have to go via 2, which is the entrance of the loop, because otherwise there is no way to reach 4. So using this property, what we will do is we will find out which is the entrance of the loop. The entrance of the loop, in short, single entry loop, dominates everything inside that loop. As you can see, that has to be the case here because that's the entrance. It's like a fortress. There's a single door to it. In order to enter that fortress, there's no other way unless you want to jump and climb the walls, of course, which is illegal. Um, you got to enter through the fortress door, and that's the gatekeeper, or that's the sentry of the region. And that happens to be 2 here for this outer loop. It happens to be 4 for inner loop. And these, the 2 dominates all the nodes within the loop. What are the nodes within the outer loop? Of course, 2 itself, 3, 4, 5, 6, 7, 8. And you can see that 9 as well. And what is the exit? What is not inside the loop? 10 is not inside the loop because you can see that there is an exit from 2 to go to 10, which is terminating the loop. So all these nodes which are inside the loop are dominated by the loop, by the header of the loop. So what is the definition of a dominator? Dominator means that a node is dominated by another node. If from root node to that node, we got to go through the dominator. As simple as that. So from 1, for example, if I had to go to any node 4, I got to go to 2. And so 2 dominates 4. That's basically what is the relationship here. So what we'll do is we'll find out these gatekeepers of the loop, which are called as dominators. And then we'll see what defines the loop using the dominators. So how can we define a loop using a dominator? That will depend on basically what is called as a package, such as this. So this is the loop over here, where my cursor is. And then what happens is once the loop is going through one execution, wants to go back to another execution, this particular package brings the control back to the loop header. And again, the same process starts of executing the loop body going forward. So this is called as a package. So what we'll do is we'll first find the dominator, then we'll find its loop using package if it exists. Note that even if a node dominates another one, it's not that for every such dominated node there is a package. For example, 2 dominates 3. But 3 doesn't form a loop with regard to 2 because there's no package from 3. However, there is a package from 9 and that forms a loop. And everything that lies between the dominator and the package, all these nodes which are there, which are reachable there from 2 to going towards 9, they will form the body of this particular loop. Okay, so to summarize this, single entry loops are characterized by their entrances, which are called as, which dominate the rest of the body of the loop. They're also characterized by the packages, which bring the control back to the headers and from a dominated node back to itself. 9 is dominated here by 2, and it also brings the control back, and so that's why this is called as a package. So what I do is on a forward path, I go from a dominated node, from a node which dominates the other node. On a forward path, I go like this. And then I reverse the direction of execution by using a package, go back to the node which dominates me. And this forms the loop body, which is a cycle, and so on. And that's how I detect all these nodes on the forward path, which bring the control towards the node such as 9. And then it loops back from 9 back to 2. So in short, the problem of detecting a loop now, okay, which is single entry, boils down to detecting a dominator and then enumerating all the nodes which are dominated by that entry point, which is 2, and then finding out the package such as 9 going back to 2, and collecting all this information which really forms the loop of this. So let's first just see um, how we can quickly see maybe what is the loop here. And then we'll go back to, okay, we don't have an example here, but let's, we can easily see here that in the previous graph itself, um, um, from the top level, I think I had already mentioned this, that the loop here is from going from 2 to 3, 3 to 4. All these are nodes are dominated by 2. So collecting all these, um, 5, 6, 7, 8, as well as 9, because you can see that the control comes here as well, finally, and this dominates that. There's no way to reach this particular one from 1 unless I go through 2. And so all these nodes are dominated by me. Now from there, I pick up a node which brings the control back to me, which is 9 to 2. And all the nodes that are on the forward path from 2 to 9, they form the body of the loop. So this forms the biggest loop outside. In a similar way, there is an inner loop from 4, form 4, 5, 6, 7, 8 is formed as a loop inside over here. So our goal will be to therefore then start with finding the dominator and then detect the package and then form a collection of all the nodes which are on the path from the dominator to the one which forms the package. So let us formally now look at this and find out how these relations are found, and then we will try to worry about the complexity of finding a dominator and how they are. The main motivation, again, as I mentioned, was that this is very fast as compared to the Warshall style of a cycle finding algorithm, which is order n cube, or theta n cube. There's no other way to find a cycle for a general graph except in theta n cube. As you will see these later, these algorithms are order n square. So we have cut down the complexity by order n here. Okay. So what is exactly a dominator in the control flow graph of another node? So you can see here the simple definition is this, that a node A in the control flow graph dominates a node B if every path from start node to B goes through A. So that's basically a gatekeeper. A acts like a gatekeeper for B. That's a very simple intuitive way to look at it, because from start node, there's no way I can go to this node B without ever crossing A. And that makes this particular region sort of secured through an entry point A. And that's when we say that A dominates B. So A is a dominator of node B. That's basically what that basically means. Let us look at this example of a dominator using some simple illustration on these graphs. And the one example I showed here. So you can see here, if you consider these different paths over here, one is dominating itself, of course, simple reflexive relation. One is dominating 2 also, because there's no way to reach to 2 from there, from 1. One is dominating 3, one is dominating 4, and so on. So the root node acts like a dominator of every node. In a similar way, you can see that there's no way to reach 3 unless one goes via 2 from the root node 1. Okay, so if I have to go from 1 to 3, Can I bypass 2? That's the question. The answer is no. We must go through there, and so 2 dominates 3. Similarly, 2 dominates 4, and so on. And 2 also dominates 10. As you can see here, there's no way to reach 10. The only path is 1, 2, and then following that is 10. That's the only way. Let's ask ourselves this question. Does 5 dominate 6 or 7? So if we had to go to 6, let's say, so the question is, does 5 dominate 6? So if you were to go to 6, you can see that the only way to go higher is 5 here, and therefore, yes, 5 does dominate 6. Now, does 6 dominate 7? If I ask another question, answer to that is no. Because if I have to reach 7, I can easily find a path from 1 to 7, which never goes through 6. So it's not that every node, of course, tries to dominate the other. There are certain nodes here which dominate the other, and you can see here that 5 does dominate 6 and 7, but 6 doesn't dominate 7, and so on. So how do we find this dominator relation? That is one question that we had to answer. And the second thing is, by enumerating this relation, therefore I will be able to find out all the nodes that either dominate me. For example, if I ask this question that who all dominates 5? The answer to that will be, of course, 5 dominates 5 itself, self-domination, and then 4 dominates it, 3 dominates it, 2 dominates it, and 1 dominates it. So it will give me a list of nodes which dominate me. So that will be one direction of relation. The second will be this, that a given node dominates which of the nodes. That's a reverse relation. So you can see here that 1 pretty much dominates everything, including itself. So the whole graph will be a set of nodes it dominates, and so on. Typically, what we'll do is we'll find out which are the nodes which dominate me, and generate that using a simple algorithm, and then use that information to find out the list of nodes which dominate me. And from there, we'll identify if there is any backage to them. Because remember that my interest here is in finding out the backage. So what is really a backage here? Let's say if I ask this question about 8, that who all dominates me? We will get an answer to that question as 1, 2, 3, 4, 5. There would not be 6, there will not be 7 in that list. Okay, so those are the nodes which will dominate me. In order to come to me, I must go via those nodes 1, 2, 3, 4, and 5. Now, in this list, in order to find a loop, the next question that I will ask is, do I have an edge from myself to one of the nodes that dominates me? If the answer is yes, which is the case here from 8 to 4, then that will define a backage. And you can see that that will now form a loop, because what will happen is the forward direction, I will come from 4 via some path. I don't know which path, that we'll worry about later. But I will come via some path from 4 to 8 because it dominates me. There is a path from 4 to 8 that is bringing the control from 4 to 8 in the forward direction. And then in the backward direction, I have this edge which is looping backwards. And together of this forward control flow and backward edge, I will keep iterating in this particular region, and that will form a loop. And that will also be a single entry loop because it will be entered through the node which dominates me, which is 4. There's no other way to enter this because 4 dominates me. If it did not dominate me, then maybe there will be other way, such as if there is an edge between 1 and 7, I could enter this, and in which case 4 will not dominate me. So in short, as long as we limit ourselves to single entry loops, they are all found using the concept of dominators, because that is where they enter, and using a back edge, that is where they loop back to the entrance. So using this, we'll find all the single entry loops. If we have a non-single entry loop, such as what I pointed out just now, one which could be entered either at 4 or at 7, that will not be found by this concept. But the question is whether such loops exist. And in fact, more importantly, even if they exist, what can we do about them in terms of transformations, etc. First of all, they are very rare. They are almost non-existent because the semantics of the languages do not allow them. And secondly, even if we have such very few non-single entry loops, the restructuring of the compiler, once you have multiple entries, is very ineffective. It cannot really do much with these loops. So we, in short, even if they are there, we just give up on them and we ignore them and move on. There will be lost opportunities. We will not touch them, we will not restructure them, we will not transform them, we will not optimize them. And therefore, we'll lose some opportunities, but there will be tremendous saving in the compilation time, and mostly they are non-existent. So in short, I'm interested in finding out, therefore, going back to the dominator relation, is who all dominates me, such as this DOM relation, which is being shown here, that the dominator set of 1 is just itself. However, the dominator set of 2 is 2 and 1. 1 dominates 2, and 2 itself dominates itself. So we are interested in finding out these DOM sets for each one of these nodes, and then finding out from me if I have any back edge to one of the nodes that dominates me. If there is an edge from me to one of the nodes that dominates me, that forms the back edge along which the control will loop. And since the other one is dominating me, there will be a forward execution path from there, and together it will form a cycle or a single entry loop. So in a sense, again, I'm interested in finding out the set of nodes which dominates me. So how do I find that out? The set of nodes that dominate me. You can easily see that this dominator relationship is a very interesting relationship. In other words, consider this small region here, 5, 6, 7, 8. And I want to find out the list of nodes and ignore the rest of the graph for a minute. Just these 4 nodes, 5, 6, 7, 8. They form, let's say, a control flow graph, and 5 being the root of this small CFG. And I'm interested in finding out the dominators for 8 here. So you can easily see here that, first of all, 8 dominates itself. So we can include 8 in its dominator set. DOM of 8 will have the node 8 in it. Now, in order for a node to dominate, you can see that it must dominate each one of my predecessors. So if I go to 6 and find its predecessor, which is 5 here, and find out the dominator set of 6 here, then I go back and find out if my predecessor dominates me. And the answer to that will be yes, that 5 dominates 6, and so does 5 dominates 7. So in other words, if I had to dictated by a certain node, it must be present in the dominator sets of my predecessors, because what will happen is if it is not present in one of my predecessors dominator sets, that means that the path can come bypassing that node to my predecessor, and therefore that node will not dominate me either, because there's no reason for the control to come necessarily via that particular node. So what I do here is the algorithm starts with initializing each one of the um, nodes of the graph as their own dominator sets. So 6 dominator set is only 6, 5's dominator 6 is 5, 7's dominator set is 7, 8's dominator set is 8, and so on. Next, what I do is I find out if my predecessor dominates me by comparing the dominator sets of those. So I look at my predecessor, which is 6, and at this particular point, its dominator set is 6. And next I look at 7, its dominator set is 7. So the intersection of these two dominator sets is null. So at this point, I proclaim nobody is dominating me. But then I move one level up and I go to 6, let's say, and I find out if my predecessor dominates me. And you can easily see here that there's only one predecessor, and if there is only one predecessor, the control must come via that predecessor. So it's which is only degree 1 as the input in degree 1 must dominate me. So that's the premise. So all the nodes which have in degree 1, such as 6 or 7, their predecessors must dominate them. Otherwise, the control will never come to them. And therefore, 6's dominator is proclaimed as 6 and 5. 7's dominator is proclaimed as 7 and 5. So at this point, now we have fixed 6's dominator as 6 and 5, 7's dominator as 7 and 5. And then we reiterate again, and I go and visit those nodes which have now degree more than 1, such as 8. And I go to the predecessors, I find their dominators and take their intersection. Only those nodes which exist in the intersection will dominate me, because if one of the nodes is absent in the dominator set of one of my predecessors, I can take a path along that predecessor and bypass that node which is absent in that dominator set. And therefore, that node will never dominate me. So therefore, by taking the intersection, now I know that 8's dominator are 8 itself and the intersection of dominators of 6 and dominators of 7, which happens to be 5. And so 5 and 8 are decided as the dominators for 8. So you can see that this process will keep working in an iterative manner, and we'll find the dominators again by using what relation? Dom of n is intersection of dom of predecessors of n. And we'll keep iterating along this relation. And by initializing all the dominators to self-dominators as per the definition, we will terminate when there are no changes to each one of the dominators. So this is a simple algorithm which is what we call as an unordered algorithm, because it doesn't assume any order of processing. On the control flow graph, initialization again starts with self-domination relation. Each dom of n is equal to n. That's where all the initialization of the algorithm happens. And then I go to the node and take the intersection of the dominators. So example here is if I take 6 and its predecessors dominators are 5. And of course, this being the only one, 5 will get added to the dominator of 6. Similarly, 5 will get added to the dominator of 7. at some point during the execution. And then whenever I revisit 8, I take their predecessors, I take the intersection of their dominator sets, and that happens to be now 5. So 5 will get added to the dominator of 8. And so finally, all the dominators therefore will propagate. So for example, 1 will propagate as a dominator to 2. In turn, it will propagate down as a dominator to 3. Because 3's predecessor is 2, and so on. And eventually it will percolate it down to 5's dominator, and 1, 2, 3, 4 will get added as dominators to 5, and therefore in turn they will get added as dominators to 6, 7, and 8, and so on. So this is again a simple unordered algorithm. The basic initialization is DOM of n is n, and DOM of n is then through an iterative procedure is set to the intersection of dominators of the predecessors. And the termination is when there is no further change in any DOM set of any node. You may think that this algorithm, of course, is kind of superfluous or is not doing the things in the right order, and you're right about that. You can see here that we could have systematically propagated the dominator sets in some ways from top to bottom. You can easily see that somehow if we had decided that we compute the dominator set of 2 first, that would immediately make 1 as the dominator of 2. And then in the next phase, we want to do the dominator set of 3, which will now put 1 and 2 as the dominator set of 3, and so on and so forth. So if we progress it along the order from top to bottom, which is depth first order in a topological relation, then the dominator sets will be computed much more efficiently as against a bottom up. Bottom up means you can see here that we computed the dominator set of 8 here as 8 itself to, of course, the initialization. But the next thing we decided to do was instead of going top down, that is from 5 down to 6 and to 7 and to 8, we decided to go bottom up. So we decided to find the next refinement of a dominator set of 8 by looking at the dominator 6 of 6 and 7, and none of them had 5 in it at that particular point because that information was not propagated. Therefore, when we took the intersection of the current dominator sets of 6 and 7, we just got null. So there was no change in the dominator set of 8 because of bottom up. Whereas if we had gone top down, we would have generated these dominator sets in a much more efficient way. Again, it's not the relation which has changed, it's just the order of computation which is different. The relation is same. The relation is we take the intersection of all the current dominator sets of all the predecessors. That is not changed at all. That is the basic premise of the algorithm or the relation which is important for computation of dominators. So that is not changed, but the order in which it is done is changed. So in short, we compute the dominator set of 2 first, and then we look at its predecessor as 1. Immediately we have 1 brought into the dominator set of 2. Therefore, when we compute the dominator set of 3, we already have 1 and 2 ready there in the 2's dominator set, which happens to be the predecessor of 3. And therefore, the flow of information is we don't do any inefficient computation in this, in which the dominator sets don't change. If they had to change, they change by following this particular order. And that algorithm is much more efficient. It allows us to flow these dominator relations along a top-down manner, which is and then traverse these. For each node, we are really computing the final dominator relationships of all the predecessors, and then only we are propagating those. That's the topological order which we are following. And because of this, complexity of this algorithm is order n. So it is linear in terms of the number of nodes for which we are computing. And we have put in a paper there by Tarjan, which has a nice explanation of this order, which is top down using depth first ordering. And the linear algorithm is what is implemented in all the compilers. Again, the relationship that is used is dominator set of given node is obtained by intersection of all the predecessors, and simply the order is what the Tarjan's algorithm carefully manages, going top down, so that the useful work is done, and that's a linear algorithm. So at this point, are there any questions about dominators, its computation, and so on? If not, then we'll move to the loop generation, which is the next thing here. Okay, and if you have further...
There is. Oh, sorry. My mouse did something weird. There's one question in chat, which is it possible to use topological order even though there's a cycle in the graph?
Yes, because the topological order is a depth first ordering typically. So you will visit beginning the root node. You will be visiting a given node before going through the cycle, and so the relationship will be given by the depth first ordering relation. So we will, of course, not revisit a particular node unless we have visited it along a depth first tree. So the depth first tree shows this particular order, and that's obviously, even if there is a cycle, it will have a unique order there that we would have visited a dominator before going to the node which is dominated, which is a key here. In which we would have already computed its dominator set in its final form without having to redo it if we had not done it in this particular order. So, and that's the order which Tarjan's algorithm first finds using depth first ordering. It then uses it. So please read this paper. It's a little bit notational coming from a theoretician, but try to understand the essence of the ordering and the essence of the argument that I just mentioned, that the useful work is being done by following this order, that the set is set to its final form before it is being used for the nodes it dominates. So that's the essence of it. Some definitions here of direct domination, which is useful in a little later in our discussion. I'll just quickly talk about that. That a node directly dominates B. Let's say A dominates B if A is there's no such thing which is in terms of domination relationship, that it does dominate B, and there is no C in which A dominates B. So that means A directly dominates B. So less than relation here shows that it is a domination relation. So so in this particular case, you can see 5 directly dominates 8. And however, 4 does not directly dominate 8, because 4 dominates 5, 5 dominates 8. So what is the sort of importance of this for our purposes? You can see that immediate dominator like 5 forms an inner sort of a region in some sense than dominator which exists at the outer level. So 4, you can see that it's slightly outside region. 5 is the immediate, although it's an acyclic region, it's an immediate sentry to my region. And this gives us a hierarchy in terms of the regions where we are entering. We first enter the loop at 4, maybe then we enter the acyclic region at 5, and so on. So the direct domination gives us some kind of a hierarchy, and also allows us to form certain properties using that particular hierarchy. And there's yet another definition which is rather simple. A properly dominates B if A dominates B and A is not equal to B. So it's basically properly or strictly dominates is the word here. So that's a simple one. That means 5 strictly dominates 8. There's no self-domination included in this strict domination relation. So now, having found the dominator relation, the next step I'll just introduce, and then we'll talk a little bit more about loop generation in the next lecture, is, as I mentioned earlier, the loop is really defined as a backage from a node which is dominated, such as 8, from the node which dominates it. So for example, 8 going back to 4, 4 dominates me and I have a direct edge to it. So since 4 dominates me, the control comes in the forward direction from 4 via different paths maybe, but necessarily it always comes from 4. That's the key here. So once it comes from 4, and then it goes back from me using an edge, backward edge to the one which dominates me, you can see that that forms a cycle because forward is coming from the dominator, back edge is taking me back to the dominator. And then within this cycle, what all is included is all the nodes which are there from the node which dominates me to which bring the control to me. So for example, 4, 5, 6, 7, 8, all these nodes, they're enumerating all different paths along which the control can come in the forward direction. And that is the region of this particular, this region of consisting of all forward paths, which are connected by the backward edge, are all forming. You can see that these are forming 2 cycles here, and in general, multiple such cycles. They are the ones which are leading to the to different cycles, which are all rooted at the single entrance, which is 4, and that's a single entry loop. So what is exactly single entry loop? It is a collection of all cycles. Again, it is a collection of all cycles which are entered exactly at one node, which is the entrance of this loop, and which are carried back through the edge, such as the back edge, which all go back and execute along that back edge. Now, if there is a node which is encountered from the dominated node, such as 4, which does not bring the control in the forward direction to 8, then it is not a part of the loop. And it's very clear here. You can see that from 4, it does dominate 9. Okay, but that 9 does not lead to any path to 8, and therefore 9 is not really part of the inner loop form from 4, 5, 6, 7, 8. So that's the important notion here to keep it in mind. And so what we'll do is we'll detect the back edge which is going such as 8 going back to 4. And then we will enumerate the paths going backward from 8 towards 4 and collect all the nodes along this path. How do we do that? That is very simple. We'll go to the predecessor and its predecessor and so on, unless the predecessor itself ends in the dominated node, the one which dominates me, such as 4. So unless and until we hit 4, we'll keep going back along both the things. And we have a guarantee that this procedure will terminate because finally all these paths must end in the node which dominates me, such as 4. So that's the way we will enumerate. We'll keep adding more and more nodes going backwards. And when we are trying to add 4, we know that, okay, we have sort of exhausted that path. We'll no longer add 4, the predecessor. So first we'll add the predecessors of 8, 6, and 7. They are not equal to 4, so we'll add them. Then we will, to the loop, we'll then take 6, we'll take its predecessor 5. We will then add it to the loop. We'll also add it for further exploration because that is not 4. We'll go to 7. We'll take its predecessor 5 that we have already added to the loop, so we'll not re-explore it. It is already added for exploration for further backward movement. So next we'll take 5. We will take its predecessor, which is 4. Now that is already a dominator. So we will not add it to the loop because it's already supposed to be a part of loop, the dominator, and the backage is already added to the loop. So we will not explore things backwards after we hit 4. And in such procedure, we'll finally enumerate all the different nodes. So that's the way we will find the loop. So we'll stop here. We'll revisit some loop finding next time and just build on this particular idea of going backwards. And thanks. We'll have no office hours in our other things. Thank you.